Thank you very much, Sir Mark, Excellencies, ladies and gentlemen. It's a great pleasure to be given the floor here tonight to explain to you firsthand how this report came about and what is actually in this report. Because often when you look at these reports, scientific assessment, many of us are scared and they would look at the front page but never open the book. That's why this is a unique opportunity for me to explain to you a few of the highlights of our report. The entire report contains 1,140,000 words. One page on your PC in Word or any other program contains about 600 words. So you can imagine how many pages the scientists have produced. That is the scientific basis, but it's equally clear that such a scientific basis needs to be communicated. That was mentioned already. And communication must be done in a condensed way, in a clear way, in an understandable way, but in such a way that we do not make compromises on scientific accuracy. That was the task that was given to us in this report. And I'm speaking here not by myself, but on behalf of my co-chair, Qing Dahe from China, and 259 scientists from 39 countries. And in fact, when you see statements that I will show you, that's not the statements of these 259 authors, but as Sir Mark has already alluded to, these are statements that the governments that form the Intergovernmental Panel on Climate Change have endorsed, word for word, line by line, in a consensus. So how did this report come into existence? It was basically a commissioning by the governments that formed the Intergovernmental Panel on Climate Change, which was founded in 1988 under the umbrella of two UN organizations, the World Meteorological Organization and the United Nations Environment Program. And it is presenting now already its 5th assessment report. The first one appeared in the year 2000. These assessment reports are commissioned by the governments. And the governments, together with the scientists, during a 2-day scoping meeting, discussed the potential content of the forthcoming report. They basically lay out the landscape which the scientists then have to fill in. That happened in 2009 for Working Group 1, 2, and 3. It was an interesting process because it gave the possibility to the scientists also to take up some new topics or to go deeper into older topics where we knew that the 4th assessment report left some question marks. One example is sea level rise. The other example of emerging new science is decadal predictability of the climate system. In other words, are we capable from the science to give you a credible prediction of how temperature, precipitation, and other parameters actually change in response to emissions of greenhouse gases over a short horizon of 10 to 30 years. That's just by way of example. We also made a conscious decision to actually include a chapter on clouds and aerosols, a well-known process in the climate system that is responsible for large uncertainties. So we wanted to make a point in 2009, and we wanted to have a sufficient number of lead authors who had actually the forum to look at that problem in great depth. Now, once you have the outline, you know, as a leadership of this report, what kind of expertise you require. So you then invite the governments to nominate people, nominate scientists who are volunteering their time and their effort into this work. It's all voluntary, unpaid service that we received from the scientists. Of course, they had their salary, but they took many, many hours, I can assure you, from extra time dedicating it to this effort. We selected 259 authors from 39 countries. It is a special characteristic of the Intergovernmental Panel on Climate Change to take care of regional balance to the extent possible. That is why we also include a large number of developing country scientists who join us in our effort. They bring unique regional knowledge to the table when it comes to assessing. Now, this work has then been carried out over the next 3 years, from 2010 essentially until just 2 weeks ago, in a very considered, procedurally clear and transparent process in which we were tasked to produce 2 draft reports. Each of these draft reports was undergoing a worldwide review. Just a parenthesis, anybody could log into that website, download the report after a declaration of expertise in climate science. So we were actually counting on the honesty of the downloader to declare before downloading that he or she considers himself or herself an expert. We were quite open. We received 54,677 comments, all of which were read by the author team and all of which were responded to by the author team. Doesn't mean that we were agreeing with the comments or that action was taken by a specific comment if there was no scientific basis for it, for example. But all of them were considered, responded to, and they will become public at the end of the 5th assessment report cycle. In total, over 1,000 experts took part in this effort. I personally know of no other scientific document on this planet that has undergone such a thorough review. But having said that, I do not claim here publicly that there will be no mistakes. It is a human effort. It remains a human effort, and mistakes may happen, but we have taken all possible care to avoid these mistakes. Should they be discovered, we do have in operation an error protocol procedure by which we know exactly what step has to be taken. First of all, a claimed error first has to be fact-checked whether at all that claim is justified. The whole report consists of 14 chapters. A few of them I have already mentioned, but essentially we have a block of chapters that deals with observations and measurements. What do we see in the climate system? What changes can we measure? And then we have a block of chapters that speak to the understanding of climate system processes. In other words, the change of greenhouse gases as they translate into temperatures. Do we understand that really quantitatively? Or what is the effect of aerosols? Do we have a good understanding of the uncertainties of all the processes that are in there? That is the second block. And the third block of chapters is the pièce de résistance, and these are the climate change projections based on multiple different methods. First of all, a large body of comprehensive climate models. 42 models were considered in a worldwide effort organized by the scientists from the bottom up with the help of the World Climate Research Program by the World Meteorological Organization. In total, we have produced or had available for our assessment over 2 petabytes of numerical data. That's a lot of memory sticks. Another innovation that I need to mention in this report is the Atlas of Global and Regional Climate Change Projections. This is basically all the numerical data for 37 regions around the world that allow the users to inspect temperature changes, precipitation changes in their region, and also receive an assessment as to the robustness of these projections over 2 time horizons from the mid-21st century one and the end of the 21st century. The second one for 4 independent emission scenarios. Again, a huge amount of data electronically available for everybody, free to use. Now, when it comes to communicating that vast amount of findings and assessment results, we have to condense it. We have to distill it. And we have 2 stages of distillation. We first distill it to a technical summary that consists of about 100 pages. But then in another step of distillation, we come up with the summary for policymakers, which only contains about 14,000 words. That is the document that Sir Mark mentioned, the document that was sent to the governments twice. Review comments were taken aboard as appropriate. And then we went through from the 23rd of September to the 26th of September, in fact, the 27th of September, 5 o'clock in the morning. Every line, every word was considered by the delegations of 110 countries, all countries that take part in the IPCC. Now, 14,000 words is still a brochure of 36 pages. And the older I get, the more I appreciate that it's hard to read 36 pages. That's why we took a conscious effort to cast the most important insights of this report into 19 key statements. Only 19 key statements. We call them SPM messages, 19 headlines. Together, they print on 1.5 page. In language that you, I hope, can understand, almost completely rid of figures and numbers. In essence, in a nutshell, the narrative of the entire assessment in 1.5 pages. The inspiration actually came from the 4th assessment report that was published in 2007. And some of you may remember one of these sentences that really stuck in our brains, and that was warming of the climate system is unequivocal. And then it goes on, of course. But that was the sentence that motivated us to go one step further, and for every section in this summary for policymaker, come up with such a clear-cut, yet scientifically accurate sentence. I will show you a few of these sentences. Let's now turn to one of the first figures, temperature change. What you see here on the vertical axis is the temperature change relative to the official climatological reference period, 1961 to 1990. So obviously you start off a little bit colder at 1850, and then you go through the century and the 20th century up to the year 2012. And what you see is very clear. It's an unusual curve for many of us because you're used to the annual mean values which wiggle up and down, but yet show the same trend. That curve is also in the summary for policymakers, but we wanted to make a point to also show decadal averages. And you see here the past 3 decades really stand out in this time series, with a plateau around 1950 to 1970, whose causes we understand fairly well, and then the temperature took off. This led us to a very simple observation and statement. Each of the last 3 decades has been successively warmer at the Earth's surface than any preceding decade since 1850. Now, this only contains one number, but it's a year, so we thought that that is fine for large-scale communication. But I tell you an interesting story during our deliberations, and that is, without naming or anything, if you want to make the top headline out of this figure, you would probably say we are now living in the warmest decade since 1850. And the scientists actually opposed this formulation, which is more dramatic, which is more attention-getting, for the simple reason that we must not base our statements on a single decade. It's much more robust to actually take together 3 decades and say these 3 decades were the warmest since 1850. And of course, we provide some additional information by just adding this word, successively warmer. So we then went back to earlier times based on paleoclimate reconstructions, tree rings, ice cores, borehole temperatures, a whole array that has become available in the last 7 years, new data, new reconstructions, that permitted us to say in the Northern Hemisphere 1983 to 2012 was likely the warmest 30-year period of the last 1,400 years. And you see here 2 words in italicized typeface, likely and medium confidence. This is the way IPCC reports are created, by also, where possible and where appropriate, convey a level of uncertainty. It's the so-called IPCC uncertainty language, a calibrated language that combines agreement and evidence into confidence, and that combines a statistical analysis into a likelihood statement. It can be likely, very likely, extremely likely, virtually certain, etc. So this is a calibrated language which basically preserves the scientific accuracy. Another figure out of the SPM now informs you how this warming is distributed over the globe. And that is the warming that has occurred over the last 112 years, basically since 1901 to 2012. And you see here that the globe did not warm uniformly, but that there is a regional pattern which is expressed in such a way that the higher latitudes on the Northern Hemisphere are a little bit more purple. That means enhanced warming due to a physical process that we very well understood and know. What you also see, and that is important, is that there are areas where we actually see a slight cooling. For example, in the region of the North Atlantic, we also understand why that is the case. But what is more important to recognize is that the cooling and the regions in the vicinity of that cooling, they do not show these small black crosses that you recognize. Meaning that the changes that we see there, that we measure there, are not significant. So only those locations that have a cross in their little pixel are actually significant changes. So it would be certainly inappropriate if a contemporary citizen here, for example, living here, would say, oh, global warming cannot happen because I just happened to measure a cooling over the last 110 years. You see another area which is unfortunately very big, and that is an area where we have no colors at all. That is where the scientists are unable to inform you what happened so far because of the absence of data, or because of the scarcity of the data, or issues with the quality. It's obvious that in Antarctica, temperature measurements are not available over the entire 112-year period, except for perhaps 1 or 2 stations, but that would not suffice to inform you about large-scale changes. Now, looking at this figure and looking at the time series before, the simple statement is warming in the climate system is unequivocal. And this is a statement straight out of AR4, unchanged and still standing. We now move on into the area of understanding quantitatively what happened in the last 50 or 60 years, since 1951. And in fact, we observe, if we look at the temperature changes, since about 1951, the planet has warmed by about 0.6 degrees Celsius. So a natural question to the physical climate scientists is, what caused this warming? And it is since 1951 that we have sufficient quality of data and amount of data that permits us to make a quantitative statement. There are many factors in the climate system that influence the temperature or the global mean temperature. Foremost, we have the greenhouse gases, and it's not only CO2, it's also methane and N2O. These together actually explain about 0.9 degrees Celsius, so even more than we observe, which has the immediate conclusion that there must be also cooling effects that bring us then down to the observed 0.6 degrees Celsius. And indeed, the cooling agents in the climate system, also emitted by human activity, are the aerosols, micrometer scale soot particles, which cause overall a cooling of the climate system by about 0.25 degrees Celsius, as you can recognize in this yellow bar. Attached to the yellow bar is a little whisker. That whisker is the uncertainty range that the scientists have assessed for the individual processes. And you see that the uncertainty in the observation is rather small because we have many observations. In the gases, it's a little bit bigger, but the biggest you see is in the aerosols. There are many processes. I've mentioned a dedicated chapter on aerosols and their interaction with the clouds, but the uncertainties are still remaining large. So let us combine now these two anthropogenic forces, a cooling forcing or a cooling agent and many warming agents into one, and we get the anthropogenic forcing, which, as it happens, explains about everything that we observe. So it's just about right. So the scientists could now say, okay, job is done. But that's not true. There are other forces that also potentially influence the temperature. And these are solar and volcanoes and internal variability. Internal variability, for example, large-scale warmings and coolings of the tropical equatorial Pacific Ocean surface, which do have a global impact. For instance, 1998 was one of the two strongest El Nino years in the 20th century and caused a temporary global warming of about 0.2 to 0.3 degrees Celsius. Not for long, perhaps for a year or so, but sufficient to make that year, 1998, a record warm year. But you see here the assessment of the scientists speaks a very clear language. It says the solar and volcanic processes are recognizable. You see that blue little bar, but they are tiny, tiny with uncertainties that are sizable, about 0.1 degrees Celsius, and the same applies to the internal variability. So even in the most optimistic or most skeptic case, you would not be able to explain the 0.6 degrees Celsius by just these two processes, solar, volcanic, and internal variability. But you do so in a physically consistent manner by considering both the strong warming effect of the three greenhouse gases and the cooling effect of the aerosols. And that is why the conclusion of the scientists reads, it is extremely likely that more than 50% of the warming since 1951 is due to the increase in greenhouse gases. We thought this is a very powerful sentence, but still rather complex to convey to the wider public. That's why we crafted an even simpler sentence by saying human influence on the climate system is clear. Now, this is a sentence anybody could say, but this is a sentence that follows from a careful scientific assessment through all the quantitative numbers, the observations, the theoretical understanding. And at the end of our session in Stockholm, this is a sentence that is endorsed by all the governments. Let us now come to the projections. You see here the global average surface temperature change, global mean again, from 1950 to 2100, simulated by about 42 climate models, the best climate models available, calculated at almost 24 centers worldwide in this concerted effort that I mentioned at the beginning. You see in gray the historical period until 2005 when the scenarios started, and these models then were forced by emission scenarios. For simplicity, we only show two scenarios, a high one in red and a low aggressive mitigation scenario in blue. They are referred to as RCP 8.5 and RCP 2.6. This is a little bit technical, but it's our identifiers for these scenarios. You see solid lines here. These are the multi-model means. If you take all the result and you just average, and the clouds that you see, the bands in red and blue, are the likely ranges that the scientists have assessed, because these models, not every model shows exactly the same evolution on a year-to-year basis. They do show natural variability, and that is captured by this uncertainty band that you see. What you see here is that the global surface temperature change for the end of the 21st century is likely to exceed 1.5 degrees Celsius relative to 1850 for all scenarios. Here is it important to recognize that what you see here as an axis is relative to the model reference period of 1985 to 2005. If you want to make a statement about pre-industrial, you have to add the observed warming from pre-industrial to 1986-2005, and that is about 0.61 degrees Celsius. So if you take the lowest scenario here, that's about just about 1 degree plus 1.6. You see that this sentence actually is a correct sentence, and the sentence was crafted with the policymaker audience in view, because our colleagues need to know something about these climate targets that have already been discussed in the framework of the UNFCCC negotiations. So we try to be here policy relevant, as is our mandate in the IPCC, but not policy prescriptive. We do not say which goal has to be reached. We are presenting scenarios. Here you see more scenarios even. That is basically a what-if information that we provide to the policymakers. We also make a statement about sea level rise. This very simple figure is one of the figures in the summary for policymakers, again for the two scenarios. And I should say this is an achievement over the past assessment report, because for the first time we combine all the essential contributors to sea level rise into our numbers. There are 4 of them: the thermal expansion of water when it's heated up, then the glaciers that melt under a warmer atmosphere, and the 2 ice sheets, Greenland and Antarctica. Now, the 4th assessment report did not include all of them, but the ice sheet, the rapid dynamic interactions of ice sheet with the temperature, were left out at that time. Due to the scientific progress since 2007, that contribution could now also be included, and therefore we have greater confidence in our numbers. Well, a very trivial, almost trivial statement here. Global mean sea level will continue to rise during the 21st century, irrespective of the scenario. So some adaptation will be necessary under any scenario, but it's a big difference whether you have to adapt to 0.45 meters of sea level rise or to 0.7 meters of sea level rise, or even, if we take into account the uncertainties, in a pessimistic case, to almost 1 meter. The choice is ours here, and that is nicely depicted in this graph. There is another subtlety that you see in this diagram, and that is the fact of the slope of the curve. Sea level rise is not over with the end of the 21st century. The slope is actually quite steep here. And with the knowledge that the ocean is a slowly responding component of the climate system, it's not difficult to conclude that sea level will rise further into the 22nd century in both scenarios. Just to give you a few numbers here, the ranges, you can just read them off from the figure, 26 to 55 centimeters during the last 20 years for the low scenario, and I have given you another number that is also in the summary for policymakers, basically a high-end number at the end here. Since we are in a time period of rapid increase, the policymakers asked us to also give the number at the year 2100, and that number is displayed here. With that, I come to the last figure of the summary for policymaker, and that is a new concept that we could bring into the scientific discussion. It reflects what the scientific community has worked on over the last 6 or 7 years, and that is the observation or the finding that there are some simple relationships even in the light of an extremely complex climate system. If you look at the cumulative emissions, that is all the emissions since the beginning of the industrialization up to now and up to a time point in the future, and take that quantity and relate it to the warming that you observe in the climate system, then you realize that this is a linear relationship that is depicted here in these various curves of different color and the clouds that you see here, which indicate the uncertainties. What the scientists have found is the higher the cumulative total anthropogenic emissions are, the warmer the planet becomes. In itself, that has been known for the past 20 years, but never in this very simple and accessible way of display and investigation. So the curves here are actually showing all these climate model simulations that I've explained to you, but now we plot the amount of carbon dioxide that has been emitted so far into the atmosphere and record the temperature increase that has been simulated in these models. And you see these simulations start at the beginning of the 20th century as black curves. The dots indicate successive decades up to the year 2010. And then you start into the colored curves, but these colored curves indicating the 4 scenarios, with red the highest scenario and dark blue the lowest scenario, they all lie roughly on the same trajectory. The only difference between these 4 scenarios is when you reach the year 2100. And of course, in the space of cumulative total anthropogenic emissions, with the lowest emission scenario, you reach that level first, here at the year 2100 for the lowest cumulative emissions, and hence also for the lowest warming. We've seen that already in the previous graph. The high emission scenario accumulates over the same time much more carbon, almost more than double the amount of carbon, and ends up here in the year 2100 at over 2,000 gigatons of carbon cumulatively emitted since pre-industrial, and resulting in a temperature in excess of 4.5 degrees. This is a diagram that I think the public can use and interpret as a guidance to what do we need to do to keep climate change limited, for example, under 2 degrees Celsius or under 3 degrees Celsius. It's not policy prescriptive. See, this axis here goes from 0 to 5 degrees Celsius. And correspondingly, the total amount of carbon that you have available to still respect that limit that you set is given here. In other words, we have a choice where our carbon emission trajectory stops on that diagram. In fact, the summarizing headline for this section is, limiting climate change will require substantial and sustained reductions of greenhouse gas emissions. How can the scientists take that conclusion, draw that conclusion from this graph? Well, for example, 2 degrees Celsius, we go and look, there are some uncertainties. We look down here, somewhere between 800 and 900 gigatons. Well, you now need to know another number, and that is provided to you in the observation section. The number, how much carbon have we emitted until now? And that number is 545 gigatons. Over half of the allotted budget for, say, the 2-degree target or any other target has already been emitted, which means that the other half, or even less, has to be or cannot more than that be emitted from now on. That is the message of this diagram, and I hope this is, in clear words, basically the bottom line. We do have a choice. Thank you very much.
Sit down.